Hey, you're here. Welcome back. This is Ruth. So now let's get on to the last part of our lecture, which is on derivatives of exponential functions. Okay, let's determine the derivative of an exponential function written as a raised to x, where a here, the base, is greater than 0 and not equal to 1. Let's write y equal to a raised to x. Then x must be equal to log y base a. Now, if you use implicit differentiation, we can take the derivative with respect to x on both sides of the equation. The derivative with respect to x of x on the left side of the equation is equal to 1, and the derivative on the right with respect to x of log y base a is 1 over y ln a times the derivative of y with respect to x. So remember, y is a differentiable function of x. So if we solve for dy over dx, this will give us y ln a. And since y is equal to a raised to x, so this should be a raised to x ln a. In particular, if the base is the Euler's number e, so that means they're taking the derivative of the natural exponential function e to the x. So from this formula that we just computed, this is equal to e to the x ln e. And since ln e is 1, that means the derivative of the natural exponential function e to the x is just e to the x as well. So to recap, the derivative of a raised to x with respect to x is equal to a raised to x times ln a, where a is greater than 0 and not equal to 1. Second, the derivative of the natural exponential function e to the x is equal to itself, e to the x. So if you think about it, no matter how many times you derive the natural exponential function e to the x, you will always get e to the x. So the first derivative of the natural exponential function is e to the x. Its second derivative is e to the x. Its third derivative is e to the x, and so on and so forth. All right. So let's consider some examples to practice using these formulas here. So let's consider y equal to 4 raised to x. What's the derivative of y with respect to x? So here, this is of the form, right, a to the x. So if we use that, we get 4 raised to x ln 4. Okay, let's take another example. So here we have y equal to e raised to x cubed. Note that this can be written actually as a composition of two functions. The outermost function is the natural exponential function, and its inner function is x cubed. So to evaluate the derivative of y with respect to x, we get first the derivative of the outer function, which is the natural exponential function. So we make use of the second formula, right? So that gives us e to the inner function, which is x cubed, times the derivative of that inner function, which is x cubed. So the derivative of that is 3x squared. Therefore, the derivative of y with respect to x is 3x squared times e raised to x cubed. Okay, let's consider another example. Let's have y, which is written as a product of 2 raised to 4x times cosecant of e raised to x. How do we get the derivative of y with respect to x here? Now, because y is written as a product, we mainly use the product rule, right? So the product rule says we have to take the derivative of the first factor, which is 2 to the 4x, times the second factor, which is cosecant of e to the x, plus you take the first factor, so that's 2 raised to 4x, times the derivative of the second factor, which is cosecant e to the x. So if we evaluate the derivatives here, so in the first term, the derivative of 2 to the 4x, so we make use of the first formula, right? And the chain rule, where the inner function is 4x. So we get here 2 to the 4x times ln 2. And then we multiply that with the derivative of the inner function. The inner function, remember, is 4x. So the derivative of that is 4 times cosecant x e to the x. Plus, so for the second term, we get 2 to the 4x times the derivative of cosecant of e to the x. This is a composition of two functions where the outermost function is cosecant and the inner function is e to the x. So using the chain rule, we get the derivative of the outer function, which is negative cosecant of the inner function, which is e to the x, times cotangent of its inner function, which is e to the x, times the derivative of that inner function, which also gives us e to the x. So we can factor out here 2 to the 4x and cosecant of e to the x. So that would give us 2 to the 4x times cosecant e to the x times quantity 4 ln 2 minus e to the x times cotangent e to the x. So we get the derivative of y with respect to x here. Now, up until now, we are only able to make use of the power rule if the exponent is a rational number. So let's take that up a notch, okay? Let's take the derivative of x raised to r with respect to x, where r here is a real number. Now, with the tools of exponential and logarithms, we can rewrite x raised to r as e raised to ln of x raised to r. This is because the natural exponential function and the natural logarithmic function are inverses of each other. Next, using the property of logarithms, we can write this as e raised to r ln x. So now we have a composition of two functions, right? The outer function is the natural exponential function, and its inner function is r ln x. So we can use the second formula. So the derivative now here is e raised to the inner function, which is r ln x, times the derivative of that inner function r ln x. Again, we can rewrite e raised to r ln x as e to the ln x raised to r times the derivative of r ln x. So that would be r times the derivative of ln x, which is 1 over x. So for the first factor here, the exponential and the logarithm are inverses of each other, so we can cancel that out. So that gives us x raised to r. So if you simplify this, we get r x raised to r minus 1 when r is a real number. So this actually generalizes our power rule. So if we state that formally, if f of x is equal to x raised to r, where r is a real number, then its derivative f prime of x is equal to r times x raised to r minus 1. So now we can take the derivative with respect to x of x raised to pi, because now we can extend this to irrational numbers as well. So the derivative here would be pi x raised to pi minus 1. We can also take now the derivative of x raised to square root of 2. So that would give us square root of 2 x raised to square root of 2 minus 1. Okay, let's take our last example here. Let's take the derivative of cosine raised to square root of 2. Note that this is actually written as a composition of two functions. So using the chain rule, we evaluate first the outermost function using the power rule here. So that would give us square root of 2 of the inner function, which is cosine x raised to square root of 2 minus 1. Multiply that with the derivative of the inner function, which is minus sine x. So if we simplify, the derivative then is minus square root of 2 sine x cosine x raised to square root of 2 minus 1. And that's it for the derivatives of exponential function. I leave you with some exercises that you can try for the lecture today on implicit differentiation, derivatives of logarithms, and derivatives of exponential function. So since we still have some time, let's try to solve number 3 here, okay? Let's find the equation of the tangent line to the graph of f of x equal to ln of quantity 2x plus 1 minus e to the 3x at the point where x equal to 0. All right, so how do we solve this? We want the equation of the tangent line. So what do we know about this tangent line? Well, first, we know that it touches the point where x equal to 0. And second, we also know that the slope of this tangent line is just the derivative at 0. Hence, we can make use of the point slope form, y minus y naught equal to m times quantity x minus x naught. For the point on the tangent line x naught, y naught, we already know what x naught is, that is equal to 0. Y naught is the function value at 0, so f of 0, if we evaluate, that gives us ln 1 minus e raised to 0. ln1 is equal to 0, and e raised to 0 is 1. So therefore, the function value at 0 is minus 1. Thus, the given point on the tangent line x naught y naught is equal to 0 minus 1. So we already have x naught, we already have y naught. All that's left to do is find the slope of the tangent line, which is actually just the derivative f prime of 0. So to evaluate that, first we need f prime of x, right? So if f of x is equal to ln of quantity 2x plus 1 minus e raised to 3x, the derivative then can be evaluated by taking the derivative term by term. If you simplify that, we have 2 over 2x plus 1 minus 3 times e raised to 3x. Thus, we can now evaluate the slope of the tangent line, that is actually f prime of 0. So this is equal to minus 1. So if we substitute this to the equation of the line, this will give us y plus x plus 1 equal to 0. And there you have it. That's the last part of our lecture for implicit differentiation and derivatives of logarithmic and exponential functions. Of course, you can go over the lecture again by replaying the videos that we have uploaded here. And if you have any questions and if you want to discuss per se, just feel free to contact me. Once again, this is Ru, and don't forget to enjoy calculus.